Hello everyone. Can you hear me?
Good evening, ma'am.
Yes, ma'am.
Okay. I'm not able to hear anyone. Just hold on. Yeah, I think now this fine. Yes. All right. Okay. Let's start the session for today. So today we are going to look into week 4, and so far what we have seen is in unsupervised learning. So even in week 4, we are going to deal with unsupervised learning. And so far, we have looked at what we called as representation learning. And next is what we learned is clustering. So when we're talking about the representation learning, we had looked at our PCA and the kernel PCA. And then we moved to, in week 3, we moved to clustering. And there we saw Lloyd's algorithm or K-means clustering method. So in this week is estimation, typically. So many of you, I mean, most all of you would have looked at this topic when you were doing stats too. So it will be more like a revision for estimation here, and just with an addition of one more algorithm that we will look in this week. So how many of you remember estimation from stats too? Okay. Okay, someone. Can someone tell me what do you understand by estimation problem?
We will estimate the parameter of the distribution. by getting some with the help of prior and the likelihood.
Okay, so you're talking about the likelihood prior distribution. So you're talking the Bayesian setting.
Yes, ma'am.
All right. So in estimation today, again, we will look into uh, two types of estimation, two different school of thoughts for estimation. You can think of it like that. So in estimation, we are going to look at one is frequentist approach, is frequentist approach, and here we'll look at the estimation using maximum likelihood. So we'll look at maximum likelihood estimation, and in the Bayesian approach also, we'll look at Bayesian estimation. All right. So here, like, okay, so we'll start with first the maximum likelihood, or before even going there, we'll talk about what do we understand by estimation problem. So, see, you have the data coming in, and let's say I have you have a set of data, which is x1, x2, so on, till xn. And we don't know, maybe we know something about this data. Maybe we know, maybe these data are coming from a Bernoulli distribution, or maybe a normal distribution, or maybe a gamma distribution, or Poisson, and so on. Maybe we just know from where this data is coming from, but we don't know the underlying parameter that is generating these data, right? So we would want to estimate those parameters. So let's say the parameter is, you can think of it as, let's say the parameter is a theta. Okay? So we want to estimate these parameters. So we want to estimate theta. So when we added the classical approach in where we are going to look at the maximum likelihood, so there we think of theta as, of course, theta is a parameter and it is not known to us. So theta is unknown. But when we are in the classical setting, we assume that this theta is a constant. It's an unknown, but a constant. But we are when we are in the Bayesian setting, we are going to think of theta as a random variable. So these are the two differences that is there uh, in maximum likelihood and Bayesian estimation. So here, given the data, we want to know, we want to estimate these parameters. So whatever given this data, whatever we do not know, we want to estimate those. And while doing this, we make two assumptions for the data that you see. So the assumption that we make is the first assumption that we make is all these xi's are independent. Um, all these xi's are independent. And the second assumption is all these xi's are IIDs, or sorry, identically distributed. Identically distributed. So in short, we call it IID, right? So what we say is our data are coming are all IIDs. They are independent and identically distributed. So you would have seen such notation. So let's say x1, x2 up to xn. So we have n data points, and we say they are IID. It means they are independent and identically distributed, and they are coming from certain distribution. Let's say I say they're coming from Bernoulli distribution, which has a parameter p, which we want to estimate. So now, like when I say independent, what does it mean? It means that occurrence of one data point is not depending on the occurrence of another data point. I mean, so all these data points are generated independently. So it's not that getting one data point in some way dependent on the other data point. And the second thing that we're assuming is all these data points are identically distributed. So if certain data point is coming from Bernoulli P distribution, then other data point that is x2 should also come from Bernoulli P. X3 should also come from Bernoulli P, right? All these, I mean, it shouldn't be like one data point is coming from Bernoulli P, other data point will come from Bernoulli Q or some normal. It shouldn't be like that, right? So what we are saying is these data are generated in such a way such that they are IID certain distribution, and we don't know the underlying parameter from which those data or points are being generated. So we want to know like how do we like what is the most ideal way or the most principled way to estimate those parameters, because what we are saying is that these parameters, so the parameter p, since this is an unknown, but it is a constant. So and I know that this p, that is probability of success in case of a Bernoulli setting, this p can be any number between 0 to 1. So I can give you 1p, maybe zero point 0.4. I can also give you zero point 0.6. Any peak can happen, right? But how do we decide, I mean, what is the most ideal p that we should take? And for that, we are going to use what is called the maximum likelihood estimate method. So before going to that, we should first look at what is the likelihood function, right? So first thing is for the max ML estimation for the MLE, the first thing is you should know the likelihood. Right? So this likelihood is basically the probability of uh, like likelihood is just likelihood of the parameter that you want to estimate. So likelihood of theta, which is likelihood of p, given that you have observed this data, this data that you have observed, and this likelihood is given by just the uh, uh, this is just the probability of occurrence of these data point, right? So this is x1, x2, so on to xn. P is the parameter. Now, since all these, I mean, this is just the joint probability. This likelihood is just the probability of occurrence of these data point or this data. Now I can say. Now, since all these xi's are independent and they're also identically distributed. So since they are independent, I can write each of the data point, I mean, each of these xi's has x1 p times probability of x2 p, so on to probability xn of p. This we are able to write because of independence condition. Right? Now, since all these, I mean, I know what is the probability of x1. So I know that this is following the our Bernoulli P distribution, right? And similarly, each of these xi's, like probability of xi's given p, is following a Bernoulli P distribution. So I can just write it as product of probability of xi's p, where I is varying from 1 to n. And now, since this, I am taking this example only, okay, and I'm just continuing over it. So if we take the Bernoulli P distribution, the data, all the data points are coming from a Bernoulli P distribution, and now you have to find the likelihood function for this, right? So what do you think should be my probability of x's?
P into 1 minus P.
Okay, so one guesses p into 1 minus p. Anyone else?
P to the power xi and 1 minus p to the power xi.
P to the power xi 1 minus p to the power 1 minus xi. Okay. Anyone else? All right. So, what do you think? Like, so, I got here two um, options for this probability of xi is given p. So, how many of you think that the first one is correct? We count. Okay. How many of you think the second one is correct? You don't have raise. All right. So one for both side. All right. Two. Okay. So I will tell you that the first one is not right and the second one is correct. So see, when here what we want is we want probabilities of x's, right? And I know that they are following a Bernoulli p distribution. Okay. So when you have a Bernoulli p distribution, so how does the PMF look like? The PMF look like e to the power xi times 1 minus p to the power 1 minus xi. Why is that? Because see, if you take like let's say you have a success, or let's take one example to understand this. Maybe you have the data point, the samples as 10101. Let's say this is a sample I have. This is the data point that I have. Now, if I have to okay, if I take x1, so this is my x1 is what? 1. So x1 is 1 means you have a success. So in that case, what is the probability of x1? What is the probability of? So here x1 is what? 1, right? So if I ask you what is the probability what is the probability of x1? And x1 is 1, it means I'm asking what is the probability of success, right? So
P
you
to
are
the
just
power.
going to write it as p. Probability of x1 is just p, right?
Why not p to the power 3? Oh, sorry.
Uh,
Yes. Yes.
mhm,
Noted.
huh, right. Now what about, so you have x2 to be 0, correct? This x2
Yes,
is
ma'am.
0. So when I
1
find
minus p.
probability of x2, that will be 1 minus p, right?
Yes, ma'am.
So what you're getting is like in case if xi's are 1, then you are just going to get p because xi's will take only the value 0 and 1, right? It cannot take any other value because they are Bernoulli. Xi will belong to either 0 or 1. Now, in case you have xi to be 1, it means you have a success. Then in that case, you get only p, right? And the other one, you get 1 minus 1 is 0, which is just p. And in case this is for when xi is equal to 1, correct? If you have xi to be 0, then what happens? Then it is p to the power 0, 1 minus p to the power 1, which is just 1 minus p. And this is basically what we want. We want this to happen. Means if you have a success, I should get the probability as p. And if you have a failure, it means if you're getting xi to be 0, then I should get the probability to be 1 minus p, right? So when you, like if you look at the first one, when you write it in this way, which is p into 1 minus p, I mean, this is not denoting what you want, right? This will all you are saying is, I mean, my probability of xi is always going to be this, which is not true because I know it can either be p or it is going to be 1 minus p, right? So this is wrong. Okay. I hope it is clear why
Yes, ma'am.
this thing
Ma'am,
is.
is my audio clear?
Yeah, it is clear.
Yes, ma'am. What I wanted to ask is, I get the get what you explained, but it very much looks like a binomial distribution. And in that case, I was wondering if xi, why don't we have that binomial coefficient before that? Because xi could be any data point. Like xi could, if xi is one, that is
Mhm.
probability of success. It could be, and there say there are 10 data points, so it could be any one of them, and therefore I think the binomial coefficient could be a useful one if you want to generalize to the whole equation. Like, it is just for one point, but if you want to explain it for the entire data set, then would there be a binomial coefficient, because it looks
Uh,
like.
uh, why do you think there should be binomial coefficient here? That's my first question.
Because
Hmm.
like, if you want to generalize, I was thinking that xi could be any data point which means success, so it could be the second one or the third one, and so the
Okay.
entire probability would be determined according to that.
No, okay. So, what I mean, this likelihood function, this we had found it for. So, what we are saying, we have x1, x2, x3, so on till xn. They are all coming from Bernoulli P. Okay, this is the idea. This is the main question over here, and we want to estimate P, and that's why we are doing the likelihood. Now, when we are doing the likelihood, till here it is okay. Now the question is, what is the probability of xi, right? So my all xi's, they are coming from a Bernoulli P distribution, correct? So when I am writing this, all I'm saying is, what is the probability? So this is basically, what is the probability of x1 times what is the probability of x2, so on to what is the probability of xn, right? This is what it means if I separate the terms, right? Now, depending on what sample you have gotten or what data you have observed, right? This is going to be each of this. So either this is going to be P or it is going to be 1 minus P. Either it's, I mean, either your x's are 1 or it is 0. So in case my xi is 0, I will get this probability of 0 to be 1 minus P. And in case my xi's are 1, I am going to get probability of x1 to be P, correct?
Yes, ma'am.
Similarly for each of this. So here again, my x2 is taking two values, 0 and 1. So it is taking the value 0 with probability 1 minus p, and it is taking the value 1 with probability p, right? So we want to write this in such a way that it it basically denotes whatever I mean, it's some concrete form or something that represent this whole picture, right? Represent this thing. So when I'm um, writing my PMF for Bernoulli, I can write it as p to the power xi times 1 minus p to the power 1 minus xi, right? Because when we do this, then in that case, I am getting what I'm saying is this will be p to the power xi. It means you will take, there are some xi number of successes and 1 minus xi number of failures. All this is all we are saying. We have n data points, and what is we are saying is some xi we have successes and some 1 minus xi's we have failures, right? So this is not binomial, correct? This what we are calculating here is not a binomial. What is binomial? Binomial is that if you have overall, let's say n trials, like if I talk about binomial random variable. So if I say I have some n trial and I want to know the number of successes to be x, right? This is number of successes. Then my distribution says you choose. uh, you choose some x out of n, and then you take p to the power x and 1 minus p to the power n minus x, which is how many times you have observed the success times the number of times you have observed the failure. And this is different from this, right?
Okay, got it, ma'am.
Hmm. Okay. All right. So we were till here. Okay. So if I have to write this, what can we do? So I'll just write it separately. So what we got is, we have uh, likelihood of P given these observed data. We got this to be product of I varying from 1 to n, p to the power xi, 1 minus p to the power 1 minus xi, right? So this is now if you want to write it as p to the power x1, 1 minus p to the power 1 minus x1, p to the power x2, 1 minus p to the power 1 minus x2 like that, then basically what you're getting is p to the power number of times you have observed the success, or number of times, if you think of it as coin toss example, then number of times you have observed the head or number of times you have observed the tails. So I'll just call it as success and failure. So if you do the product, what you're going to get is at the end, you are going to get p to the power number of successes, okay, and 1 minus p to the power number of failures. That's fine. Okay. So now, as we know, to find the likelihood function, or sorry, to find the maximum likelihood estimation, what we need to do is, so for MLE, what we say is my P hat ML would be arc of max of likelihood, right? So I want that P which maximizes my likelihood function. Okay. So you have to now maximize this likelihood function over P. All right. So one easier way to do it is, of course, using the log function, because I know that log is an increasing function and I can, like, maximizing this function will be equivalent to maximizing my log function. So we can take the log. So I take log of L, just write log P. So you will get what? Log of P to the power ns, 1 minus P to the power area, right? So I can write this as ns times log P plus nf time log 1 minus P. Now I will have to, since I want that P that gives me the maximum likelihood, so I will have to differentiate with respect to P and equate it to 0. So I do, let's denote it as maybe small l, okay? So I do dl upon dp. So if we do that, we get ns upon p plus nf upon 1 minus p, and you have minus 1 over here. And I equate it to 0. Okay. So what do we get? We get p times 1 minus p. So just, okay. So I get ns times 1 minus p minus p times nf. This is equal to 0. And this is what? This is ns minus p times ns minus p times nf. So this is basically um, n of s minus p of number of successes plus number of failure, right? And number of successes plus number of failures is going to give you just n. So what do we get? We get rp to be number of successes by total number of data point. And this is what I got it as p hat ml. So if I have a Bernoulli random variable, my data points are coming from a generated from a Bernoulli distribution with some parameter p. Then what we got is the best estimate, I mean the maximum likelihood estimate for my p is nothing but number of successes by number of by total number of data points. It means number of times. If I talk about the coin toss example, it means number of times head occurs divided by total number of times we have uh, thrown the uh, we toss the coin, right? So
Same
this
as
is
the mean,
hmm, same as
mean,
the
mean, mean,
mean of
mean of the data.
yeah, correct. Sample mean you're talking about, right?
Yes, ma'am.
Hmm.
Sigma xi upon n.
Correct, correct. Yeah. And this is nothing but sum over xi to n divided by n, which is sample mean, as we all know, sample mean. All right. Hope you got the idea how to work with it. Um, so this was for a Bernoulli random variable, and we can do this maximum likelihood process for every other distribution in the same fashion. Okay? So I will not do any other distribution for now. I would recommend you to really go back and practice if you have forgotten on how to work on it. So similarly, you can do it for other distributions also. All right. So next, we are going to move to okay. So see, Bernoulli was my discrete random variable, right? But when we have some continuous data, I mean, when your data set is generated from some continuous random variable with some parameters, then in that case, we will take the PDF, right? Now it is no longer probability of a point. Now we will talk about the PDF. So that you should take care. And one more thing, like if you have the data points, suppose x1, x2, up to xn, they are coming from certain distribution which has two parameters. For example, you let's say they are IID and they're coming from a normal distribution. And I know normal distribution has two parameters, which is mean mu and variance sigma square. So in this case, I will have to estimate both my parameter. I will have to estimate my mu and I will have to estimate my sigma square. Then how do we work on that? So when you are finding, let's say mu, when you're finding mu hat ml, then in that case, you treat your sigma square as a constant and then differentiate with respect to mu and you get mu hat ml. And when you are finding your sigma square ml, then you differentiate your likelihood function with respect to sigma square and you treat mu as a constant and work on it. All right. So I would
Ma'am,
say, hmm,
ma'am, there's a lot of background interference, so I'm just going to make it quick. Ma'am, here we are doing estimation of
hmm.
from a given data set, but what if we just use the given data set to create the distribution instead of finding the best one that fits it? Why can't we just since you are giving the example that it already comes from normal distribution, can't we just figure out the mean of the data set and put a distribution on it?
You're saying, can we not figure out mu and sigma square if we
Yeah,
know
yeah,
that's
from the data.
normal?
Yes, ma'am.
Okay, from the data, how will you figure out where the mean is and where I mean, what the mean is, what the variance is from which this data set is generated? This is just one sample that you have observed, right?
Okay. Okay, so it
Yeah,
might
this is
be
just one.
it might have a issue like because it's a sample, it's a smaller subset, so there might be issues.
Hmm.
Is that what you're saying?
Yeah, yeah. So in like in many cases, when you find we get the best estimate that I get for my mu is generally sample mean, but not for everything. You cannot get it for all the distributions. For example, I think if you take if let's say your data points what you have observed, if it is coming from symmetric, in that case, that's not. I mean, you're not going to get your P as sample mean. It doesn't happen for all the cases. So this is just one sample that you have observed, and from what distribution it has come from. Okay, I am saying this, so this distribution is coming from. But what are the parameters that are generating those data points? This is what you have to estimate. And to estimate, we are using this data set that we have observed.
Excuse me. Excuse me.
Hmm. Hmm. Yes.
Hello.
Hello.
Yeah, I was wondering. So here we calculate U hat ML, and then for the sigma square ML, we use that U hat ML.
Yes.
Okay,
Hmm.
thank you.
Okay. So I think to brush up some numerical problems from likelihood, you can go back to your stats room and just pick up some problems and try to work on it. It will be clear. Maybe if you're facing any issues, yeah, we can discuss it again in the next class.
Ma'am, are we going to get the similar type of questions in MLE in, from a
Uh,
specific?
no, I don't think so. Or maybe or maybe not. Depends.
Okay, ma'am. Or ma'am, or you don't want to disclose?
No, I mean, it can be similar, it cannot be similar, depends on the person who prepared. So,
Means the questions are from the distribution or it will be random.
sorry, will the question be from?
Distributions or it will be from random.
We don't know. We don't know that. We don't know anything about the question.
Okay, ma'am.
Okay. All right. Let's focus here now. So this was about your maximum likelihood estimate. Now we will go and see what is called as Bayesian estimation. All right. So as I mentioned before, I mean here also the idea is the same. What we want is we want to estimate our parameter from which uh, from which we believe the data set has been generated. But when we were looking at the maximum likelihood estimation, there we had what we had said is my parameter is though it's an unknown, but we are saying it's a constant. But here it is unknown, and what we are saying is my parameter theta is a random variable. You will have to treat theta as a random variable. Now, when I'm saying my theta is a random variable, so it will have any random variable will have some distribution, right? So this this theta will also have some distribution that will follow for theta. And in Bayesian estimation, we are going to see three terms over here. So the first term that we'll see is what we call as prior, which is like the prior knowledge or my prior belief about the parameter. Then likelihood, which we had seen earlier also. And then next is the posterior. And there is something which is evidence. So evidence is just the data set. So it's basically these three. We'll go back to it later. So what we are saying is I have like before even you see the data set, let's say you have some belief or some faith or some knowledge about your parameter, and that prior knowledge, that prior belief that you have is what you are calling it as prior distribution for theta. So prior distribution. This is your belief about the data set. What do you think? Maybe I can say that maybe this theta is coming from a normal distribution, or maybe this theta is coming from some beta distribution or Bernoulli distribution. This is my assumption for this theta, right? Then after I make the assumption, I whatever assumption I have for this theta, then next we see the data set, right? Next we see the data. And once I see the data, then I will have to update my belief about the parameter that I had made. So that update you are doing, whatever update you are doing. So my prior, let's say my prior distribution was this. So, and then you see the data. So after you see the data, you need to update your belief about your parameter. So that is what we call it as posterior. The probability of theta given that now you have observed the data. So now you have observed the data. What is the probability of theta now? And this is what we call it as posterior. Okay. So so you have prior, you got the data, and now you just have to update your posterior. So this is what is happening in Bayesian estimation, basically. So if I think of, so you have what you have to find, you have to find your posterior, right? You have to like once you have observed the data, you need to find your probability of theta. So you have to basically find the posterior. So you want to find what is the probability that what is the probability of theta given that you have observed the data. Okay. So what is Bayes theorem? So let's say if I have two events, this is my Bayes theorem. So what does Bayes theorem says? If I have two events A and B, then probability of A given B is nothing but probability of B given A times probability of A divided by probability of B. This is Bayes theorem. So now we are going to use the Bayes theorem over here, all right, to find the posterior. So what we want is we want to find what is the probability of theta given that you have observed the data, right? So this is using the Bayes law. What you will get is what is the probability of observing the data given this theta times probability of theta divided by probability of data, right? And what is the data that we have? The data that we have is so that is x12 xn, this is my data set. Given that you have theta times probability of theta, and this is probability of theta divided by probability of theta, which is again x1 to xn. All right. And as we have seen, that's this probability of theta is nothing but our prior. This is the prior distribution. What we had believed my theta would have come from. So this is my prior distribution. And if you look at this term, this is nothing but what is the probability of observing the data set. And this is your likelihood. Yes. Okay. So this is my likelihood. And this is what we are calling it as evidence. So since this does not depend on theta, I can choose to ignore this. So this is what we are calling it as evidence. This is nothing but probability of occurrence of the data set. Since now the theta is nowhere here in the picture in the denominator term, this is just a constant. You can think of it as now that my posterior is proportional to likelihood times the prior, right? And this is what we are going to use for finding the posterior for any problem that is in Bayesian estimation. So you will have some prior belief about your parameter. You will observe the data, and then you can calculate the likelihood. And now once the data has come in, you want to now update your prior, and that can be given by just prior times the likelihood. It is just proportional to prior times the likelihood. So any problem that you have, you can solve like that. So, so one example that is given in your lecture. So there, what we have said is, suppose I have um, my prior belief that the data is coming from maybe it has a distribution like this. I mean, my parameter has a distribution like this, let's say, where it is speaking at maybe 0.9, this 0.9. And now what we are saying, we observed some data here. So we observe some data set. Maybe in this data set, we have most of the values as 1, sorry, 0. Uh, okay. Oh, sorry. Let's say this is my this was the distribution of my theta, suppose. Okay. And then you observe the data, observe this data set. So if you look at this data set, and if I am trying to estimate the P for my Bernoulli P distribution, then if I look at this, maybe here only um, 2 out of 10 samples are only my success, right? So it will be more like closer to P. So once I observe this data, now I will have to update my belief about the data. So initially my graph where it was peaking at 0.9, now it will somewhat shift towards the left. And it will be more closer to maybe zero point 0.2, zero point 0.3 or something, right? So the distribution may shift like this. And the peak is at maybe 0.25. So this is my posterior. So once you had observed the data set, you have um, you will have to update your belief about the parameter that you had, right? And let's say this was one example where you saw a sample in such a way where most of it were failure. But let's say if you observe the sample in such a way where you actually get out of 10 samples, let's say you have only one failure. This is out of 10. Okay. So out of 10, if you have only one failure, it means your actually nine data points that you are observing are success, are all ones. So it is actually what your belief was about the parameter. And when you observe the data set, again, you saw that some 9 out of 10 samples are my ones. So this is kind of supporting your belief. So now when you get the posterior, you should get a sharper jump and a sharper peak at this point 9. So your posterior for, the distribution that you will get for your theta or p will now be more, it will be more sharp, right? It will be more sharp at point 9. Something like this it will go. So this is like this data set is like supporting your prior belief. So now you can more with more confidence you can say that you have the parameter p that you have is actually p should be zero point 0.9, right? So this is the idea. Now, if we go ahead and do one more problem, like your data set is again all the Bernoulli setting. Um, so we had, let's say, your data set, which is x1, x2 up to xn, and they are coming from Bernoulli P, right? So since we are talking about the Bayesian estimation, your P should have some distribution, right? So that distribution, it can follow any other distribution, right? So let's say the distribution that I'm going to take for P is beta distribution with the parameter A, comma B. Okay. So why did we take first of all beta A, comma B? We could have taken anything else, right? So see, we wanted to my parameter here is P. And P I know should always lie between 0 to 1, right? P always lie between 0 to 1. So I will have to look at that class of distribution which lies between 0 to 1, right? So beta A comma B is one choice because when I talk about the beta distribution, I know that my beta distribution is always, this always lies between 0 to 1. And how does it look like? This looks like x to the power alpha minus 1, 1 minus x to the power beta minus 1, divided by, of course, some normalizing constant we will have, which is beta of alpha comma b. Okay, so this is, we can ignore that this because this is normalizing constant. Now, and this exercise over here, this belongs to 0, comma 1 when I'm talking about a beta distribution. So this is one choice for prior, right? So one prior that you can take for P is beta AB. What do you think you can take? Do you have any other idea what other prior distribution can I take? Any guesses?
Binomial.
Uh, so does binomial lie between 0 and 1?
Could it be a
Uniform.
uh, uniform distribution?
Uniform between,
0 and 1.
yes, uniform between 0 and 1. That will work. Even you can take Bernoulli P, right? The most obvious choice here, Bernoulli P. That will always lie between 0 and 1. Yes, you can think of more. So these are three like very obvious choices that we know from our distributions. So
It
these
could
are a good
even be, it could even be a normal distribution between
uh,
0 and 1.
normal, but okay, if you so what you're talking about is truncated normal in that case.
Yes, ma'am.
That should work, but you should take the truncated normal. All right. So what we are going to do here is we are going to choose my prior distribution for P. So prior for P to be beta A comma B. So why are we choosing why this is chosen for Bernoulli P is because this is a conjugate prior. So if you remember this, conjugate prior means that if if you choose your prior to be if you choose the prior for P to be beta AB, if this sorry, if they choose the prior for P to be beta AB, then your posterior will also be a beta distribution with just some change in the parameters. Okay, and that is why such since your belief was that my P is coming from beta distribution, and given that you have observed some data set again, when you are updating your belief, observing the data set, again you're going to get a beta distribution. So this is quite, I mean, simpler to work with because you're not changing any distribution. All you're changing is some parameters over here and there. So that's why beta AB is mostly used when you're working with the Bernoulli P distribution. Okay, so we are going to look at this, like how this posterior will come out to be. So let's do it.
Ma'am, could you just scroll up 1 second?
Yeah,
Ma'am, in
yeah.
the graphs that you showed, ma'am, no, the graphs, yes, ma'am. Ma'am,
Mm,
since this is the graph of the parameter, right? So because the parameter is a like a function,
mm,
therefore
mm.
it could take any value between 0 and 1, and therefore the x-axis is also like x-axis is like any value between 0 and 1.
Correct. Yeah,
Yes.
x-axis is any value between 0 and 1.
Yes, and and the y value is also any y-axis is also a value between 0 and 1, which is the probability or the
Uh,
density.
mm, Density. This is density, right?
Yes, yes, ma'am.
Yeah.
So
So
the
this is my P,
yeah,
and this is my FP of P.
yes, ma'am. Right, and ma'am, I don't get what you said about the beta distribution. I get that we are
Mm,
having a prior and we see the data and according to it we update our beliefs, but
mm.
why suddenly we chose the beta distribution and what exactly is the
I will.
beta
I'll.
distribution? I don't get it,
Yeah.
ma'am.
Yeah. I will show you. So that is what we are working. We'll do it now. So yeah. It's all right, Priyanshu. Okay. So all right. We have the data set. So we have x1, x2 up to xn. They are IID Bernoulli P. Okay. Now here my P is a random variable. I'll just make it a little bold. So my prior for P, I'm going to denote it as this is f of P is x to the power alpha minus 1, 1 minus x to the power beta minus 1. And this is my beta distribution. Okay. So here my x lies between 0 to 1 and alpha beta greater than 0. So since we have written P, let's stick to P here. So p to the power alpha minus 1 and 1 minus p to the power beta minus 1. Now you have observed the data, and when I have to find the posterior, posterior would be, as we had seen before, that this is going to be proportional to prior times the likelihood. Okay. So what is the prior distribution here? My prior is p to the power alpha minus 1. So this is p to the power alpha minus 1, 1 minus p to the power beta minus 1. Okay. Times the likelihood. Okay. So my likelihood is, I mean, my samples are coming from Bernoulli P. So this is going to be product of p to the power xi 1 minus p to the power 1 minus xi. I is reading from 1 to n. Okay. So this, I mean, we had written this as what? So p to the power alpha minus
Um,
1. Yeah.
this prior distribution,
Mhm.
this PDF, this should be proportional, written as proportional, or
Which one?
prior, above
Prior.
P.
Yes.
This should be
This one?
proportional
Yeah,
with,
yeah. This is proportional. It is not exact. Yeah, yeah. It is not exact. I mean, you have some normalizing constant over here
thank you.
because you divide it by the beta function, right?
Yes, ma'am, thank you.
Yeah. Okay. So, all right. So you have p to the power alpha minus 1, 1 minus p to the power beta minus 1. And here, what you have? You have p to the power xi, and this will happen for p to the power. I mean, how many times will you get it? So this will be more like x1 plus x2 plus up to xn, right? We can write it as p of xn, sorry, x1, 1 minus t to the power 1 minus x1, t to the power, or maybe we'll stick to our number of successes, number of failure part. So what were we saying here? We were saying that this is nothing but p to the power number of successes into 1 minus p times number of failures. Right? So this is going to give you p to the power ns plus alpha minus 1 times 1 minus p to the power np plus beta minus 1. Right? So if you look at this, again, the structure, I mean, this shape looks like a beta distribution, right? Because you have something to the power, uh, something to the power alpha or a minus 1 and 1 minus x of something minus 1, something of this kind, which is nothing but our beta distribution. So we started with the prior, we started with our beta distribution, and when, after observing the data set, again we reached at a beta distribution. So this is again a beta distribution. And what are the parameters? The parameters would be number of successes plus alpha, comma, number of failures plus beta. All right. So we started with prior and we reached at, oh, sorry, we started with beta and we reached at the beta distribution only. So this is what we are saying is my posterior. So my posterior is proportional to beta distribution. This is basically beta distribution. So once I know that my posterior is also beta distribution, how do I estimate those parameters? Okay. So there are two ways in which you can estimate your parameter p. So one way is to find the expectation of the posterior.
And why have represented number of failure as NP?
Oh, sorry. Yeah, let's do NF. NFS. So one way is to find the expectation of the posterior. So now you have posterior distribution, you will have some, and whatever expectation that you get for this beta, we can say we can estimate our P using expectation of posterior. And then the other way is to find the map estimator, which is also called the maximum maximum okay, a posteriori estimator, which in short we call it as map estimator. And this map estimator, so this p hat map is nothing but you have to find that p, so arc of max of posterior over p. So whatever p gives you the maximum value of the posterior, that you take it as that is what we call as a p hat of map. So this is just arc of what is posterior. Posterior is probability of theta given that this data set over p. So these are two ways. So like once you know what your posterior is, then to estimate the underlying parameter from which the data set is generated, you can use these two ways. So one way is you find the expectation of the posterior, and the other is you find the map or map estimator, map of maximum posterior estimator for P. So these are two ways in which you can do it. All right. Any doubt so far?
Ma'am,
Mm.
ma'am, since you talked about truncated normal for prior, can we say that we
Mm.
can take any distribution and truncate it within the specific range?
Yeah, you can truncate any distribution. That shouldn't be a problem. Have you looked at truncated distribution?
No, ma'am.
Maybe you can explore it a little if you are interested. Okay. So
Ma'am,
any doubt?
after
Mhm.
getting this posterior,
Mhm.
what was your last remark
My
for
last
getting?
remark was so from posterior, what you are getting? All you are getting is that your theta follows this distribution. After seeing the data set, this is I'm saying that my theta follows a beta distribution with these parameters. So once you know the distribution for a theta, maybe if it's a beta distribution, uh, so you will have between 0 to 1, right? So maybe you can have something like this, or maybe something like this, or any shape. I mean, beta takes different shape within 0 to 1. So something you are getting here. So some posterior distribution you got, and that posterior distribution is what we're saying is we got it as beta. So all we have gotten is the what is the distribution for theta, right? So that is not my goal. My goal is to estimate this parameter. I want to know what this p is, right? So now all I know is the posterior from my prior. After hours of the data, I find the posterior. Now, after I found the posterior, now my goal is to estimate p. So there are two ways in which we can do it. One is that you find the expectation for this posterior. So if you have a beta distribution, so for beta distribution, what we know is that its expectation is expectation for the beta distribution is
Alpha by
given
alpha
by
plus beta.
alpha by alpha plus beta. So in this case, it will be ns plus alpha by alpha plus beta plus ns plus nm, which is n. This is my expectation of beta. Or the second way is that you find the that p that gives you the maximum posterior. So that is one way to do it.
Okay, ma'am. Thank you.
Okay. Anything else? Okay. So again, you can work on some problems also. I mean, you will have you have a lot of questions in activity and practice. We can just go through it and see if you're able to do it. So, all right. So what we have seen so far is like the two ways for estimation. One is the maximum likelihood estimation, and the other is the Bayesian estimation. Now, we will look at the estimation problem for a little complicated data. So here in week 3, we had looked at clustering, right? So now in that setting, how can we use this estimation? How can we use estimation over there? And what else can we say from there? Right? We want to know on that part. So let's say if you have, or I will just write it here only. So now we are going to talk about mixture of Gaussians. Gaussians. So I think you have looked at this in MLF also, I guess, on in the last week, if I'm not wrong. Mixture of
Yes,
Gaussians has
ma'am.
been
Week
done.
12.
Week 12 last, not in much detail, but this has been done. Okay. So before before what we saw is our data set are coming from certain distribution and we were estimating it. Now here we are just saying maybe my data, the data set that I'm seeing is coming from some complicated data you have. Now, how do you deal with it? So if I have, let's say, some data points over here, some data points over here, and some data points over here. Okay. Uh, I have this data set. So how can we estimate? Um, how can we estimate the parameter, or how do we like before estimating? We should know like from where does this data set coming from? So this data set, if I assume that it is coming from whole R, I mean, this is my real line on which I have represented my data set. So one very natural distribution that comes to my mind is the normal distribution, right? Because I know the normal distribution has nice bell-shaped curve centered at mean, and it takes the value throughout R. So if I am assuming that, let's assume that my the data set that I'm seeing is coming from a normal distribution with mean maybe some mu, so some mu and some sigma square. All right, but if I look at this data set, I mean I can see that these three data points and these three data points, though they are occurring, but if I assume this distribution for this data set, then in that case, all I'm saying is that these points are coming with a very low probability, right? So they are in the low probability region. So this doesn't look ideal for us, right? This is not what should be an ideal model for the data set. So what we can do instead is we can since wherever we see this data set, I can make a peak over that data set. I mean, so if I can make it as like this, then again it goes, then again I have a peak coming in over here, and then I have something like this. Okay, maybe something like this. So here you can see that my data set, whatever is occurring, um, so they have like peak at those points, right? So this is more like mixture of Gaussian distribution. So maybe this is one Gaussian curve. This is the other Gaussian curve that you're getting, normal curve. And this is another normal curve that you're getting. So you have here three different normal distribution. And what we are assuming is my data set is coming from a mixture of Gaussians, where I can say maybe this is a normal distribution with mean maybe mu1, variance sigma 1 square. So this is some normal distribution with mean mu2 and variance sigma 2 square. This is my normal distribution with mean mu3 and variance mu sigma 3 square. Okay, so we can think of it like that. So here, um, what is happening is like um, first, like given any data set, right? If someone gives me a data point, the first question that should come is like which mixture should is my data set coming from, right? So which mixture is xi coming from? Because that is also important here because my data set are coming from three different normal distributions. It's a mixture of normal distribution. So if I get a data point, I should first thing is which mixture density, which mixture, which distribution it is coming from. And once you know which mixture it is, then you will have to like calculate the probabilities and so on, and then you can do it. So you think of it like, so you have here x1, x2, x3, maybe this is my x1, this is my x2, this is my x2, this is my x4, x5. Just think of it like that. 7, x8, x9. Now each of these will have the indicators, or maybe instead of doing this, we should do it random, maybe. So maybe call the first one as x1, maybe this is x2, maybe this is x3, maybe this is x4, this is x5, this is x6, this is x7, this is x8, this is x9, right? So each of these xis will have some, like when we were looking at clustering, we were talking about the cluster indicators for which we were representing as zis. So even here we can represent it as zi. We'll stick to the same notations. So here what we are saying is that my z1, and so my z1 is going to be 1. If I think of it as the first cluster, I mean, this is my second cluster, this is my third cluster, we think it like that. So my z1 is going to be 1, my z2 is going to be 2, my z3 is going to be 1 again, my z4 is going to be 3, cluster 3 it is coming from, right? So this is how you can just think of all the zis. And what we're saying is that I have here in general 3, but this is for this example, we have 3. But if I have, let's say, in general, K mixture. So in general, when you have K mixture, then each of these zis that you get,
This
this,
Z1 is the indication for the cluster now.
yes. So in
Then
this case, this is just a mixture, which mixture it is coming from. Yeah, tell me what was your doubt?
not get that, ma'am, because this Z1
Hmm?
is indicator of first cluster, Z2 for the second, and Z3 for the.
No, it is not that. So when I say cluster indicators, so you have to think of it as a pair. So you have X1, you have Z1, you have X2, you have Z2. So on you have X3, you have Z3, you have X4, you have Z4. So for
It
each
is
data point,
indicating that X.
yes. So though this Z1, I mean I'm writing it as Z1, but each of these Zi's will take only three values that I know because I have only three mixture here. So either it can come from mixture one or mixture two or mixture three. So that's why I've written it over that all the Zi's belong to 1 to k. So for this example, my Zi will belong to 1, 2, 3. But for every data point, you will have a Zi. For every Xi, you will have a Zi. But each of these Zi's will belong to 1, 2, so up to till k. It depends on how many mixtures do you have.
Ma'am, I am unable to find a difference between Jedi and Jedis and CIs, Z1 and clusters.
Z1 and cluster, okay. Okay. So your doubt is that there should be only Z1, Z2, Z3. Is it what you are saying for this example? Is this a doubt that according to
Yes,
you
yes,
there should be only
yes,
Z1,
ma'am.
Z2, Z3? Okay.
Yes.
So that is why I was writing it here that this is for each of the xi. For each xi, you will have a zi. It means
And
so.
ma'am,
What does it? Hmm.
what we call this Jedi as?
These ZIs are cluster indicators. So when we are talking about the clustering, these are called cluster indicators, right? And so here it is a mixture indicator.
And that is difference from CIs, clusters.
What is CI?
Means cluster name we have seen in the previous lectures.
So here it is not a cluster, right? It is now a mixture indicator. So there we were getting different clusters, right? So when we're talking about the clustering, or maybe we got three cluster. So this is cluster one, cluster two, cluster three. So I was writing Z as cluster indicator. It means which cluster my IO data point is coming from. But here now I have mixture of Gaussian. So this ZIs will represent which mixture it is coming from, right? So for every XI you will have a ZI. So if you complete this, see, these are my data points. I mean, my X1 is this. So if I have to write Z1 for my X1, if I have to write Z1, so now see, my Z1 value should be what? Since Z1, my ith data point, that is the first data point, is coming from my first cluster,
Yes,
right? This is
ma'am.
my
That should be
first
all.
cluster. So that is 1. Okay. Now, where is my X2? X2 is here, right? So my Z2 should be 2.
Two.
Now, where is my X3? X3 is here,
Yes,
right?
ma'am.
So what should be my Z3?
It should be three.
It should be 1, right? Because it is coming from the first cluster.
Yes,
My
yes,
third
yes.
data
Sorry.
point, it is from
Yes, yes.
first cluster.
It should be
What
one.
about, yeah. Now my X4 is here. So it means my fourth data point is in the third cluster or third mixture, right? So my Z4 should be 3.
Three.
Where is my Z5? Z5, sorry, X5 is here.
Okay. Yes,
So
in
Z5
second.
would be second.
Two.
So you see that all these ZIs, that is Z1, Z2, Z3, Z4, Z5, so on till Zn, Z9, all even though I have Zi varying from I varying from 1 to 9, but I can see that it can only take three values. It will either take one, or it will take two, or it will take three. It cannot take anything else. These ZIs are just to denote, I mean, if I'm writing ZI, it means I am saying I'm writing this ZI for my data, ith data point, that is Xi. I mean, which data, I mean, my ith data point is coming from which mixture. So if I write, give some Xj to denote which mixture this Xj is coming from, I will write Zj, right?
Yes,
This
ma'am.
is just the notation.
Thank you.
Yeah. Okay.
Yes, yes, clear.
Hmm. Okay. So, okay. So now what we are saying is, suppose that probability that my Zi is taking some value L, I will denote it as IL. So this is the probability that what is the probability of ith data point coming from clustered L. So that is given by pi of L. So let's say if I have n data point, so and I have k cluster. So what is the probability that my Zi, so if I have to write for I, so what is the probability that Zi is equal to 1? It means what is the probability that my ith data point is coming from cluster 1? So that would be pi 1. If I write what is the probability that my ith data point is coming from cluster 2? Cluster 2. So that is my pi 2.
Right.
What is the probability that my Zi is coming from cluster 3? So that will be pi 3. So in general, for some L, I mean, I know that my Zi can take value from 1 to k because I'm assuming k mixtures. So probability, so this L will always lie between 1 to k, either between 1 or 2 or so on till k. So probability that any data point is belonging to mixture 1 or mixture 2 or mixture 3 will be given by pi 1, pi 2 or pi 3 and so on. Okay. And all these pi i's, so this pi I should, the condition is that all these pi i's should lie between 0 to 1, and the product of all these, the sum of all these pi i's should be 1.
Ma'am, sorry I
This
missed it,
is
but
K.
what are these pi eyes?
Yeah, this pi i's are, what is the, so if I look at this, so I'm saying what is the probability that my ith data point is coming from mixture L, assuming my I have k different mixtures. So what is the probability that my ith data point is coming from mixture L? So that is pi L. So if you look at this example, so here to think of it, what is the probability if I take any xi? So what is the probability that my z1 is if I'm writing z1, it means I am saying my first data point. I'm looking at my first data point. Okay. So what is the probability that my Z1 is coming from mixture 1? So that I will give by pi 1. What is the probability that my Z1 will come from mixture 2? So that I will denote by pi 2. And what is the probability that my Z1 is coming from mixture 3? That I will denote by pi 3.
Ma'am, so these pi eyes are posteriors.
Pi i's are, they're not posterior. I mean,
What do they denote?
see, they're just probabilities, right? So, see, I mean, if you look at the first mixture, I mean, it can go on. I mean, it is never zero, but it is going towards zero. After three sigma, it almost go to zero, but never zero. So, if I take my x1 only, if I take my x1, so you can see that, I mean, you will have all this, right? I've not drawn the figure properly, but you can see that probability of my first data point coming from the first distribution is pi 1. I mean, this is the PDF for this, right? So what is the probability that my first data point is coming from uh, mixture 1? So that is given by pi 1. What is the probability that my first data point is coming from the second distribution? I mean, you can see that it is never zero, right? It is never zero. It is, even if it's very less, you have this probability. So what I'm saying is that probability is pi 2. And the probability that your uh, x1 is coming from uh, mixture tree is pi 3. Is it okay?
Could you, is it possible to use some examples, numeric examples?
Numerical example. Yeah, I don't have the numerical example right now. Um, but okay.
Ma'am, any random example?
Yeah, yeah, okay. Just okay. Let's draw this figure again. Let's see. So I will again talk about k is equal to 3. It means you have three mixtures. Uh, suppose that you have, let's say it is maybe -5. Let's take it as 0. Take it as 5. Okay. So you have the distributions. Okay. These are the three normal distributions that I got. It's not 0. Okay. Um, now suppose, and these are, I mean, -5, 0, and 1 or 5 are the means that I've taken for these three normal distributions. Now assume that you have observed some data over here, some data over here. Okay. So maybe think of it as what it can be, maybe -3, something. So now if I, so it's -3. So I will have some pi 1, I will have some pi 2, and I will have some pi 3. So what I said is probability of Zi equal to L should be pi L. And the assumptions are that sum over pi i's, where I varying from 1 to k, should be 1, and all of these pi i's should lie between 0 to 1. Now, okay, so if this is the data point that I observed, so what am I saying? Um, what we are saying is that sup- we want to find what is the probability of xi to be -3. Okay. You can see from here that you have three mixtures. So this is more like law of total probability is what you will use here. And this will be given by probability that my xi is equal to minus 3, given that it is coming from M1, mixture 1, times probability of mixture 1, right? Plus probability of xi is equal to minus 3, given that it can come from mixture 2. Because even if you look it over here, you can see that, I mean, all these distributions, I mean, for minus 3, we will have all the three distributions. I mean, I cannot say for sure, I mean, there is no 100% probability that your minus 3 point is coming from distribution 1. It is not for sure, because it can also happen that this minus 3 can come from second mixture, or it can come from third mixture. It just, the probability is quite less, but there is still a chance that it can come from these two mixture also. So this is mostly law of total probability. I mean, this is what you do. So if you have to find the probability of this point, I will use all the three mixture. So I'll say probability of xi is equal to minus 3, given now m2 times what is the probability of m2, plus probability of xi to be minus 3, given it is coming from m3 times probability of m3. So now I should know what is my probability of m1, what is my probability of m2, and what is my probability of m3. So for this data point, I am so what I'm saying is that probability this of m1 is what I'm calling it as pi 1. This probability of m2 is what I'm calling it as pi 2. And probability of m3 is what I'm calling it as pi 3. Okay.
Right.
So
Yes.
yeah. So is it okay now?
Yeah, ma'am. It's better. So,
Hmm.
ma'am, what could be the possible it would be anything from between 0 and 1, like a
Yeah, and everything should add up to one. I mean,
okay,
you can take it anything. I mean,
okay,
any possible choice.
right.
If it is a
And
numerical problem, these will be given to you. Uh,
yes, okay. And ma'am,
mhm.
shouldn't there be something like divided by the total probability of the three,
This is the law of total probability, right? What do you divide? You don't divide anything, right?
like the probability of M1 plus M2 plus M3 or
Why
something?
it should be, what is the law of total probability? What is the probability of event A? It is just probability of A
Oh,
given
yeah,
that,
right. Ma'am. Yeah,
yeah,
I got it. Yeah, probability of given.
law of
Yes,
total
yes.
probability. It is
Okay.
not Bayes' theorem.
Yeah, right. Yeah, right. Yes.
Hmm.
Yeah.
Okay. Um, all right. So we stopped at where? We stopped at let's assume that for any data point, my Zi, any data point, probability that the I data point is from class mixture L is pi L with these assumptions. Now, uh, once this is done, then I need to, once I know uh, like what are the probabilities from which this data point can come from. Then next is I know the distribution for all these x's. I mean for all these mixtures. So I will generate my x's according to according to this normal distribution, because normal distribution and mu of zi. So these are the mixture indicator, this zi, comma sigma square of zi. So if my I data point was from Z1, I will generate from a normal distribution with mean of mu Zi and variance of sigma square Zi. I mean basically that particular mixture from which that data point is from. So this is what you have to do here. So here, one thing is like the data. I mean there are two terms here. One is the observed data, and the other is unobserved data. So observed data is what I mean is your xi, so x1, x2, up to xn. So this is what you have observed. And what you have not observed is those zi's. You don't know from which mixture, I mean, someone has just given you this data set, but you don't know from which mixture density it is coming from. So you don't know these underlying zi's. You don't know your z1, z2 till zn. So these are unobserved, something that you did not observe. And these are latent. These are called latent variable or also called hidden variables. So these zi's are called the latent or hidden variables. Okay. Um, so now from here we are going into something which is a very popular algorithm in machine learning, and it is called the EM algorithm. So I don't think we have enough time to do this today. So maybe I'll stop it over here only. The EM algorithm is what we can look at in the next class because this is from where it is starting. Uh, so in this example, like this mixture of this mixture of Gaussians, how many parameters? How many parameters do you have to estimate? Like
Just,
in previous problems, we just have either one or two, but
Two.
how many do we have it here?
ma'am, it would be like if there are three mixtures, so six
Hmm.
parameters.
If there are three mixtures, you have six parameters. Okay.
So it would be like
Anyone else?
k k times two or something like that. If there are k mixtures.
Okay. Yeah. Anyone else? How many parameters do you think we have to estimate it over here? See, if we are saying that we have k mixture, so for each of these mixtures, I'm saying they all are coming from a normal with mean mu and mu k or variance sigma k square, right? So if you have k mixtures, you are going to get 2k parameters, one for each mixture. Sorry, two for each mixture. So you have k mixture, you will get 2k parameters. Now these are there, I mean that you have to estimate. But apart from this, there are more. You have these pi i's, right? Where I is varying from 1 to k. You should also you will also have to estimate your pi 1, pi 2, so on till pi k. So how many are these? These are again k. So you will have k. But there is one restriction. What is the restriction? The restriction is that some of these pi i's, where I is varying from 1 to k, should be 1. So if I know my k minus 1 pi i's, then I can predict for sure what is my pi k. So this is not k. You have to estimate k minus 1 estimator, 1 k minus 1 parameter, right? Because sum of pi I should be 1. So if you know k minus 1 of pi I, you can tell for sure that what is your pi k, right? Like for in this example, if let's say I give you pi 1 to be 0.5, pi 2 to be 0.4, then I can tell, right? That means pi 3 should be zero point 0.1. This is not something that we are predicting. All we have to predict is these two parameters. So I will have to predict pi 1 and pi 2. Okay, so that is why k minus 1 parameter. So in general, overall, I will have to estimate 2k plus k minus 1 parameter, which is 3k minus 1 parameter is what you will have to estimate in this example. And for this, I mean, to estimate these parameters, we will use our EM algorithm. All right. So I think this is where I will stop here. Any doubt so far? Were you able to understand whatever we have discussed today?
Yes, ma'am. Yeah.
Okay. All right. So EM algorithm is like completely new topic, so I will not start it now because it will take quite some time.
Hello, ma'am.
Yeah.
Actually, I want to ask one thing that there are a lot of PYQs questions,
Mhm.
and while solving these questions, we come up with some doubts.
Okay.
So where we can mm, discuss this type of questions, PYQs.
So you can discuss it in the TA session that happens, or you can also discuss it on Discourse.
Okay, thank you, ma'am.
Okay. Yeah. Thank you. All right. So shall I stop it over here now?
Yeah, you can, you can.
Hello,
Yes.
ma'am. So I had a doubt like when we calculated by total probability P of xi,
Mhm.
and then is it before that that we're saying that xi comes from the normal mu zi and sigma square zi, or like
Yeah. Yeah. Yeah.
can
Because if given any if you have any data set, when you get any data point and you want to find the probability for that, so you need to know like before I have like I mean this is something that you know from before that you have some k mixtures and each mixture is a normal distribution with some mean and some variance, but you don't exactly know what are these parameters. Like what are these pi i's and what are these sigma i's and mu i's.
so the mu, like are we using, how are we estimating that? That is where the EM algorithm will come in.
That is where EM algorithm will come. Yeah. So I will find the likelihood. You will find the likelihood, and then again we will proceed to EM algorithm.
Okay, okay.
Hmm.
Thank you.
Yeah. Okay. Okay. So I'll stop the recording. So next would be Friday, right? So yeah. So yeah. Before the Friday, I mean Friday is